Okay, I'm going to show you another example on how to approach this conjugate beam method. Before that, I would like to mention a few things about the previous example. So we got two answers for the deflection and the slope in terms of EI, but I think we have not used the sign convention to indicate whether this deflection is upward or downward, or the rotation is clockwise or counterclockwise. So before I start doing the next problem, I'll take you to the slide where we discussed about the sign convention. So the sign convention is, if the positive ordinates of the MOE diagram are applied to the conjugate beam as upward, then a positive shear in the conjugate beam denotes a positive slope of the real beam. So now, for example, if the load is upward, then it's going to be upward. Now, if you consider the shear, say positive shear in the conjugate beam denotes a positive slope of the real beam. So if your slope is counterclockwise, then it's a positive slope. If it is clockwise, it's a negative slope. And a positive bending moment in the conjugate beam denotes a positive deflection of the real beam with respect to the undeformed axis. So in that perspective, if we look at here, so considering this situation, the MC is clockwise. So generally, when you take equilibrium condition, for example, if I show here, I marked here as counterclockwise positive, because this is sagging positive. So here this is going to be a hogging moment. So actually I assumed a negative moment. Okay, I assumed a negative moment and I got a positive value. So I got a positive value for MC. So which means the delta C is going to be a negative, so it's going to be minus 54 over EI. Slope also, the shear, normally the positive shear is clockwise rotation, so we mark the shear like that, positive shear downward. So here I marked upward, so I kind of marked in the opposite direction and I got a positive value, which means if based on sign convention, the shear also should be a negative, deflection also should be a negative. That means the deflection is downward and the slope is clockwise, because for a clockwise rotation, for a counterclockwise rotation, we got this 24.8. So these two values will be applied with the minus value. So for example, if I have marked this RC downward and MC counterclockwise, I would have got a negative value here. Okay, so which means it's a downward deflection and clockwise rotation. Okay, so so that's why you have to mark it in a proper direction, proper way, so that you can eliminate this sort of confusion. So now, since I have marked in the opposite direction, I got a positive value. So means, now for example here, the rotation MC is rotating, it's in this direction, and so I got a positive value, but clockwise moment is kind of a negative bending moment. Okay, so that's why you need to, I think in the next example we'll choose the right one. So here we have a beam and we have to use conjugate beam method to determine slope and slope at A here and displacement at C here. So we know that in a real beam a real beam's slope and deflection is equal to conjugate beam's shear force and bending moment. So if I plot a conjugate beam for this loading arrangement, then the shear force I obtain at A for the conjugate beam will be equal to the slope at A. The bending moment I obtain from a conjugate beam at C will be equal to the deflection at C. Okay, so the first step is to derive moment diagram. So I'm going to show you how to plot this bending moment diagram. So here, if you look at this one, A, C, B, and you have a 4 kilonewton load. So basically, since this load is symmetrical, without doing much, I can sum all the forces vertically, F, Y. So if so sum of F, Y is equal to 0 upward, then I'll obtain RA plus RB is equal to 8. Then horizontally, sum of Fx is equal to 0. Then if I take moment by A, so you have RB into 8 minus 4 into 2 minus 4 into 6 is 0. So 4, 4, 2, 2, 2, 3. So you get RB is equal to 4 kilonewton and RA is equal to 4 kilonewton. Even without this equilibrium condition, I can obtain that, but just for clarity, I have done this one. So now, if the beam is in equilibrium, all parts of the beam or section of the beam also in equilibrium. So to plot a bending moment diagram, I require how the bending moment will vary between A and this point. So I'm going to mark this one D, and this is E, where the loading is acting. So between A and D, and D and E, and E and B. So I need 3 sections to plot the bending moment diagram. I'm going to get only bending moment diagram, not other. So x greater than 0, less than 2. So this is a typical section. So I mark mx. So mx is, so this is the distance x. So mx, if I take counterclockwise positive, mx minus 4x is 0. So mx is 4x. So if we consider x greater than 2, less than 6, then I have this 4, I have the other 4 also acting on this. So this is the typical section. So mx, and this is the distance x. So again, if I consider counterclockwise positive, mx minus 4x plus 4 into x minus 2 is 0. So mx is 4x minus 4x plus 8. Okay, so that becomes 8. So then if you consider x greater than 6, less than 8, then you have 4, you have the other 4, you have another 4. So here is the typical section where you have mx. So counterclockwise positive, so mx minus 4x plus 4 into x minus 2. So this is 2. So this is x, and this is 4. Okay, so 4 plus 4 x minus 2 plus 4 x minus 6 is equal to 0. So in that case, mx is 4x minus 4x plus 8 minus 4x plus 24. So 32 minus 4x is the bending moment equation. So if I plot bending moment diagram 0, 2, 6, 8, 0 to 2 it's 4x, so at 0 it's 0, at x is equal to 8, so it's a linear curve. Okay, so linear curve, 8 kilonewton meter, and then between 2 and 6 is a constant 8, and if you substitute here 6, so 24, 32 minus 24, 8, and if you substitute x is equal to 8, it's 0, so it becomes again a descending curve, the negative tangent. So this is the bending moment diagram. Okay. Kilonewton meter. So now what we need to do is we need to apply this as a load to a conjugate beam of this real beam. So conjugate beam, if you have a pin, far end pin support, it's going to be a end pin. You have an end roller, it's going to be end roller. There are no other supports. So basically the conjugate beam of the real beam, so if you plot this one, so here it's going to be pin, here it's going to be roller, and this is the load you're going to have on this. Two, 6, 8, C. So A, B, and C. So this is the load. This is the load, actually M over EI. So this is the bending moment diagrams, and if you divide this by EI, you get a similar shape. So 8 over EI, 8 over EI. So this is the load. So it's on the positive side, so it's upward sign convention. Load acting upward. So if I take equilibrium conditions, I can find RA so I can apply equilibrium conditions, and sum of all the x direction forces are 0, so HA 0. If I sum all the y direction forces to be 0, so then I have RA plus RB minus the load due to this load. M over E diagram is half into 8 into 8 over EI. Okay, half into 8. So total base and the vertical distance 8 over EI. Okay, so this is the area is equal to 0. So that is RA plus RB is equal to 32 over EI. So since it's metric, so RA is equal to RB is equal to 16 over EI. That is the load acting, the reaction at A and B. So now if I consider a section, the reaction at A is equal to the shear force at A. So this is the RA is upward, so this is going to be, say, if you consider this is an upward shear, is a positive shear. So shear at A of conjugate beam is equal to 16 over EI. Therefore slope at A is equal to, so that is theta A, that is equal to 16 over EI. So now I need to find the bending moment at C. So what I'm going to do is I'm going to take an arbitrary section here and derive the bending moment equation, and then when I substitute x is equal to 4, I should be able to get the bending moment value because x is at 4 from A. So this is the arbitrary section. So this is the 16 over EI and that x, and you have the load acting upward. Okay, I made a mistake here. Okay, that here RA plus upward, RB upward, and this is also plus, and this is minus, this is minus. So this is also minus, and this is minus. So the slope is minus 16 over EI. Okay, minus 16 over EI. So that means clockwise slope at A. Okay, so minus 16 over EI. So now for example, if you take the real beam, it bends like this. Okay, so the rotation is clockwise. Rotation is clockwise. Okay. So that is what this minus 16 over EI means. Now if I take here, so I have to put mx. Okay, so positive moment is 0, so I have mx minus 16 over EI. Actually it is minus 16 over EI, right, because I put upward and it's a minus, so I have to mark it correctly. So minus 16 over EI, because I marked it upward and it's a minus 16 value, so that's why mx minus 16 over EI into x, that is the moment due to this load. Then you have let me break into two components. I take the triangular component, so that is again minus half into the base is 2, so this is 2 into, so 8 over EI, so 8 over EI, and the point of action of that is 2/3 distance from the top. So it's going to be, the distance is x minus 2/3 of 2, so that is 4 over 3. So x is the distance minus, this is the 2 meters, so 2/3 of that 2 is 4 over 3, so x minus 4 over 3 is the distance from the point of action here to that distance. So this is the distance, this is x minus 4 over 3. Okay, I'm going to erase that one. That is due to this triangular load, and then this rectangular load is again minus x minus 2 is the base into 8 over EI is the height, so that is the area, and the effect, the effect, where this load will have that effect is half, so half of half from here, so it's like x minus 2 is the distance and divided by 2. Okay, so you get an equation mx is equal to this one becomes x minus 2 squared into 8 over 2 EI, okay, plus 3x minus 4 over 3 into 8 over EI minus 16 over EI into x. So that is the equation. So it's in the second order. If you plot the shear force diagram, we can plot the bending moment diagram, but that's not my interest. So I need to find MC, that is where when M is equal to 4. So 4 minus 2, so 8 into 4 minus 2 squared over 2EI plus 8 into 3 into 4, that is x is equal to 4 minus 4, 3 minus 16 over EI into 4. So 4 minus 2 is 2 into the 2, 4, so 8 into 4, 32 divided by 2, so 16 in EI plus here 12 minus 4, 8, so 8 into 8, 64 over 3EI minus here 64 over EI. So if we take a common base EI, it is 16 plus 64 divided by 3, that is 21.33 minus 64. So that is 16 in plus 21.33 is 37.33 minus 64. So if I calculate 16 plus 21.33 minus 64, that is 26.67 minus 26.67 over EI. So MC at conjugate beam is equal to theta C in real beam, that is equal to minus 26.67 over EI. We substitute the values E and I in kilonewton and meter, because all the loads are in kilonewton and the distance are in meter. So if you convert E and I in terms of kilonewton and meter, and if you substitute, you'll get the deflection, not theta C, it's delta C, because this bending moment gives you delta C in real beam is minus 26 over EI, so that you'll get some value in meter or millimeter, and that's a deflection, and the deflection is downward, so downward deflection. So with this there are two more problems. I think this is going to be your card, and I'll put it here. So now I want to tell you one thing. This is a problem that I will consider as part of your continuous assessment, because now the continuous assessment has changed. Now there is no tutorials happening, and there is no in-class tests happening. No, and the computer labs, we will be arranging some way of doing computer labs, and the mid-semester is going to be an assessment based mid-semester. So I will give you some marks towards a continuous assessment for this problem. So here you can see that determine the displacement at D and the slope at D, okay, at this point. Assuming A is a fixed support, B is a pin, and C is a roller, use conjugate beam method, and you know that there is a F value. This force is from your student number. So you have a student number, something like EN some number, and the last digit say 1 2 2 3 whatever. So the last two digits, say if it is 23, okay, if your last digit is 23, your F is 2 plus 3 5 kilonewton. Suppose if your last digit is 6 plus 3, then it is 6 plus 3 9 kilonewton. So you get your relevant f value using the last two digits of your student number, and sum those two digits, you get your load. You apply that load and you work out this problem, and you do it in a paper and take a snapshot or a scan using your, there are a lot of apps available in Android like cam scanner or something like that. You can use that to scan it or take a snapshot it, and then you have to upload this to a folder. So this folder will be available from tomorrow 1 p.m. till, so tomorrow means, what I mean is say this is posted on Thursday, this is on Thursday early morning, so tomorrow means Friday. So you have to upload between Friday 1 p.m. till Saturday 8 a.m. So, okay, so 8 a.m. Saturday. The problem will appear tomorrow, so tomorrow morning the problem will appear. So you have time, a lot of time, to work out this problem and scan and upload to the courseware. Okay, and I normally allocate 5% marks combining several class tests and class exercise towards your CA. Now if you consider your CA, 10%, 15% is from mid-exam, then you have 10% from project and another 15% from computer lab and other exercises. So normally I give 10% to the computer lab and 5% for this sort of exercises that we do as we progress through the class. So this could contribute towards that, some part of that 5%. So it's essential that you do this problem and upload before Saturday 8 a.m. and the problem will be available to you from tomorrow morning onwards, so you can work out and upload using the conjugate B method. And then I have given another problem here as a homework, so you can try this by yourself. Okay, try by yourselves. Okay, so try by yourselves, and if you have any questions on this one, you can of course ask me, or you can of course contact me and write to me or speak to me. So there are several modes of communications. Okay, so with this I complete this section, and when the next lecture I'm going to upload is on slope deflection method. Okay, so let's wait for that lecture. It will be uploaded in 1 or 2 days. And in the meantime, if you need any clarification, please do not hesitate to email me on my email address. Okay, for any queries. Thank you.